right, John. I haven't had any questions. Y'all have particular questions you want me to look at? Make sure I get your names for you, Lee, okay? I think I have several of you marked down, but not everybody. Particular, what you got? Spring 22, number 13. Y'all feeling okay about this exam?
How many questions are they going to make?
You know, normal, 28. Well, that is your 8 free response and 20 multiple choice. So it's always the same. Okay, you'll have one like this, number 13. The hard part about this one is just making sure that you get the figure drawn correctly. So just be careful. I always like to draw a figure. I really recommend that you do that too. And then also recognize this is an electron. I don't know if yours will be an electron, but anytime you see a negative particle, make a big circle around it or note that somehow, because usually you'll go through the problem and then you might forget. So do something to help you to remember that. It travels in the y direction, so that's my velocity vector, in a region of a uniform magnetic field that's directed in the plus x direction. So that is B. And then I do the right-hand rule. I let my index finger go in the direction of B, my middle finger goes in the direction of B, and then my thumb gives the direction of the force, which would be into the page, except that it's an electron, so it's going to be out of the page. But I'm pretty sure you have one like that. Likewise, number 16, where, let's just go and do this one while we're here. And you have a similar one here in your free response, right? Your free response has one where you have a wire and you have to determine the direction that the force is applied to that traveling charge. So here I have a velocity vector that is in that direction and a force vector that's in that direction. That means that I have to have a magnetic field that is into the page, like that. That's my magnetic field. If I do my right-hand rule, remember, thumb is your force, V is your index finger, and B is your middle finger. So here, V, F is my thumb, and so my middle finger points into the page. So my magnetic field has to be into the page. And then I can use my third application of the right-hand rule, where my fingers go into the page on this side, and they wrap around. That means that my current is to the right. So my current here is to the right. Make sure you know those right-hand rules. Make sure you practice them, because there will be, gosh, 7 or 8 times where you have to apply it, either for just particular questions like these, or in the course of the question. All right?
Like the trajectory of the arrow is what gives you the force in that direction.
That's right. Yeah. So remember, as you have a particle that enters a magnetic field, a charged particle, it may follow a path that looks like that. The force is always perpendicular to that path. So here the force would be in that direction. Here it's in that direction, in that direction, and in that direction. The velocity vector, by the way, this is the force. The velocity vector is tangent to the path. So the velocity vectors are like this. Notice that this is always 90 degrees. This is the velocity vector. And in this case, I would have a magnetic field. My magnetic field would be out of the page. So this is a positively charged particle traveling in a region of magnetic field that is pointed out of the page. Let's see. Magnetic forces are centripetal forces. Okay. Emily?
Go over some of the ones with the wraparound right-hand rule?
Sure. Yeah. I mean, this was one, number 16, where it was combined with the others, but there, like number 14 is a good example of that, where I just want to know these 2 wires generate a magnetic field, and I want to know the direction of the resulting magnetic field. I did one similar to this in class yesterday. If you remember, I had the 4 wires and I asked for the direction of the force on the 4th wire. This was a little simpler. Let's take this one on the right first. My current is coming out. That means that my magnetic field wraps around in a counterclockwise direction. So the magnetic field goes in a counterclockwise direction, like that. Now if I expand that circle, if I expand that circle, it goes counterclockwise like that. At the point P, at this point, I get an arrow or a vector for the magnetic field that is in that direction. I don't recommend that you draw those circles that way, even though it might help you to see it, but it just makes your page really messy. And so what I recommend is that you draw a radial line. And at point P, I know that the magnetic field either has to go in that direction or that direction, because those are lines that are tangent to that circle, okay? They have to be perpendicular to that radial line. And so I think about, well, if it's wrapping around in this direction, that means my vector is in that direction, down and diagonal. So the magnetic field due to that wire is going to be in this direction. And then I can do a similar thing for the other wire. The magnetic field due to this wire was into the page, so the magnetic field wraps around clockwise, so at point P, it's going to be pointing in the same direction as that E vector. So the net magnetic field is going to be the sum of those two vectors, or vector D. There are some others. It comes up a few times on the exam. 17 on this. Oh yeah, this is one similar to the one that we did in class yesterday. So let's try it out. I'm going to draw our radial lines out, goes into the page. So the vector due to that wire, the magnetic field is in that direction. Draw a radial line like that. It's going to be, what, in that direction. And then it's going to be in that direction. So I have those three vectors. Y'all see how I drew those? Notice I draw the radial lines. I think that's better. And the magnetic field vector is always perpendicular to that radial line, because that is a tangent line to the circle that represents the magnetic field going around. So now, as I look at these, I see that the net magnetic field is going to be up, or excuse me, I'm looking for the force, but the magnetic field is up. So I have a magnetic field that's up. I have a wire that has a current that is out of the page, and I want to know the force acting on that wire. Current is my index finger, points into the page. The magnetic field is my middle finger, so that means that the force that acts on this wire is going to be to the right. Force acting on it is going to be to the right. So there are two steps there. You first had to figure out what was the net magnetic field by drawing these three vectors and then realizing that the x components of these two vectors cancel out. So my vector is pointed up, and I just redrew it over here. This is that wire at point A, and it experiences a force that's to the right. A lot of right-hand rule stuff on this exam, so make sure you practice that. If you're doing some last-minute studying, that's what I would recommend practicing. Plus the free response, make sure you get all that. I mean, that's eight questions. That's 25 points on them. So. Okay, so if you want to write this on your fingers, that's fine. Or there are two applications, right? F equals QVB, and then F equals ILB. Those are the two equations, and the right-hand rule that's associated with it, V is your index. So if you're writing this on your finger, you just write a little V on your finger, all right? B is your middle. That's true for this one too. I is your index. And then F is your thumb. Okay? So if you want to write that on your hand, that's fine. So I'd have V and I, F and B. I got that? Okay. Okay, I was just looking at it. What about 19? So on number 19, I have a magnetic field that's out of the page. So this is B. I have a velocity vector. Let's just pick a point. Doesn't really matter. And at the bottom there, the velocity vector is to the right. So I have V. I know that I have a magnetic field that's out of the page. So I would expect on this particle a force that is downward. I would, except as I look at this path of this particle, I know that there's not a force pulling downward, but instead there's a force pulling upward, a centripetal force towards the center of the circle. So then I know that the sign of that charge is not positive, it's negative. And because the force is opposite what I would expect just from looking at the figure, as a negative charge. That's a good example of a spectrometer. That's how a mass spectrometer works, that it makes those particles move in a circular path, and it measures the radius of that path to find out the mass to charge ratio. Other particular questions, y'all? Like here's some with mass spectrometers. You'll see these. Your mass charge ratio, identifying the particle, that's where you're calculating the mass charge ratio. Remember your cyclotron equation, mv over qv. Isn't that right? I think that's right. I always have to return back to the original definition. That is that the magnetic force is equal to mv squared over r. Yes, that's right, mv over qv. That tells you the radius of that path in the cyclotron or in the mass spectrometer. They're the same, those two things. And allows you to calculate the mass to charge ratio. So m over q, if I solve this for m over q, it's rb over v. So r was 4 times 3 divided by 2. It's a 6-to-1 ratio. All right? Number 18. We've done that a number of times. It's just where you're solving for the mass charge ratio and then identifying the particle. Well, this is my family. That's me and my wife, and that's my son, and that's my daughter. That actually is her name, but it just sounded like a particle. We ate a particle.
For some of your older exams, I know we've been doing refraction. Is there anything with mirrors that's going to be on the exam?
Yeah, let me show you what you'll have. So for mirrors, you won't see spherical mirrors, but the only thing for mirrors that you'll see is one like number 16. We've done that one in class.
Will there be any of, like, I guess the concept ones? Like, I think it was 17 or 16. You had more, like, concept ones based, or, like, one was standing. What would you experience through refraction or reflection?
Let me look at it. I think that's the only mirror question that I had.
Like number 16 on screen 21, there's a angle question.
Yeah, you'll definitely have one like that.
Or in the paper, I wasn't.
Yeah, number 16. No, is that really the only mirror problem that I gave you?
There's also one on
No, I'm looking at your exam for tomorrow, so. Yeah, that's the only one regarding mirrors. Is one
I
on.
just saw some mirror ones had more concept, and I was like, I don't really think we got into
We didn't really do. I think that we did finish that concept test. It is on Moodle or on Canvas, but no, that's the only mirror question that you'll see.
Yeah, that's
You know how to do that. You know how to do that one. Yeah, it's just really
So,
angles, right?
number 19 too, right?
Number 19 has to do with. I know it says reflection, but it's really refraction.
great.
So with number 19, that's really just a special case of the law of refraction, where that theta 2 is equal to 90. So I would say n1 sine theta 1 equals n2 sine theta 2. But I would let theta 2 equal to 90 degrees. So this whole thing goes to 1. And then I'm solving for theta 1. Theta 1 then is the inverse sine of n2 2 divided by n1 and solve that. And then, if you get an error in your calculator, it's probably because you're moving from low index to high index. And when you move from low to high, you don't get total internal reflection because the light bends towards the normal instead of away from the normal. In this case, you will get total internal reflection because this light ray, as it moves out here, it does bend away from the normal, and it has to bend away in order to have this angle of 90 degrees here, this refraction angle. I know we call it reflection, but it's really a refraction phenomenon.
And it equals 1, like for air, for example, you know that it's going to be 90 degrees, like outside of the
In order for you to get total internal reflection occurs when this angle is 90 degrees, but it doesn't always occur. It depends on this angle, because if I have this small enough, the light will just go out. But if I have it shallow enough, it will refract so that it goes at 90 degrees. So it doesn't have to occur, but what I'm asking here is what is that angle in order for it to occur? Okay. Other particular questions? Yeah. You're going to see stuff about the index of refraction and the speed of light and ranking those things and which one is going faster or slower. So make sure you dwell on those for a bit. We okay with those? You need to know what, yeah, come on. Number 18 on this exam? I don't remember. Perhaps. But you do need to, so here, you do need to know the wavelength and the color. So the longer wavelength is the red light, the shorter wavelength is the blue light. That's what it's asking here. And so the color that would be bent or refracted the most is the one with the higher index of refraction. So that's the blue light. You do need to know your electromagnetic spectrum too, by the way, right? And so know that electromagnetic spectrum, gamma rays, X-rays, ultraviolet, visible spectrum, which in this case would be the opposite of what you did, and then infrared, microwave, and radio. I think y'all know that. That's very cool stuff. But know that the order of that in wavelength, frequency, and energy. All right. Particular questions? Yeah.
Yeah, spring
20?
20. Question 11.
This one about the magnetic field? How far from the straight wire? Yeah. So remember, if you look on your equation sheet, you'll see two equations. N mu naught I over 2R and B equal mu naught I over 2 pi R. Those look really similar. You need to know which one applies in these various cases. This one right here has to do with a loop of wire, and the way I can tell is because it has an N in it, which tells me the number of loops. This one is for a straight wire, and that's what I have here. I have this long straight wire. It has a current of 0.45, so I have 4 pi times 10 to the minus 7, that's on your equation sheet, times 0.45, that's the current, divided by 2 pi, and then R is the distance from it. Oh, that's what I'm looking for. I'm looking for R, and it has a magnetic field of 0.04 Tesla. So then I solve that for R. I don't know what the answer is. Do you know what is that answer? C. So that would be 2.3 times 10 to the minus 6 meters. And so the answer would be C. If I solve this, R would equal to 2.3 times 10 to the minus 6 meters. You will see one of those, and or one with the loop. I don't remember if I had both, but you'll definitely see one or more of those. I mean, one of those is on your free response, right? Because you have to calculate the magnetic field due to that wire, and then calculate the force that that particle feels due to that magnetic field. So one of those is on your free response. And remember on that free response, I want to know both the direction and the magnitude. So make sure you list both of those correctly. All right, others? Number 12? Okay. Okay, this one's meant to be easy. I think a lot of people missed it though. I have this wire between the poles of a magnet. At that location where the wire is, what's the direction of the magnetic field? The magnetic field just runs from north to south. So the wire is irrelevant. Doesn't really matter about the wire. But the magnetic field runs to the right. Magnetic field always goes from north pole to south pole. Okay? Others, Joe? Number 9. Okay. Which of these statements about the magnetic force? Look, you will have just basic stuff about magnets and magnetic force. Make sure you review those in your notes. The magnetic force is parallel to the magnetic field. Now remember, F, V, and B are always orthogonal. That's the whole point of the right-hand rule. So that's not true. The magnetic force is always opposite the electric force. Could be, but it doesn't have to be. That the electric force has to do with the electric field, the magnetic force has to do with the magnetic field. So not always, can be. The magnetic force can change the energy of a particle. No. Centripetal forces only change direction. They don't change the speed. And since we don't change the speed, we're not changing the energy. So it's a centripetal force. Centripetal forces don't change the energy. All right, Joe. Other questions? 16 on this exam? Okay, so here I have, this is a three-dimensional drawing. First of all, recognize that the magnetic field runs in this direction, that's B. And then let's just take the right-hand side. So on the right-hand side, my current is going in that direction. So I have a current that is into the page, and a magnetic field that's to the right. That's this left-hand side of the figure. Current into the page, magnetic field. That means that this part of the wire will feel a downward force. This part of the wire will feel an upward force. Down, up on the right, that means it's going to move counterclockwise. This loop of wire sitting in a magnetic field will move counterclockwise when you put a current through it in the direction shown.
How do you know that it's coming out or coming in?
So the way that I draw it, and if my 3D figure confuses you on the exam, please just ask me. I can always show you. See, this wire has this arrow coming out this direction, and this had an arrow going that direction. So this is out of the page, this is into the page. It goes in a loop. So it's different direction on either side. But again, if my figures ever confuse you on the exam, you can always ask me. I'll clarify. Always ask questions. I might not always answer them, like if it's something that's, that you should know as I'm assessing, but you can always ask. Don't be afraid to ask. Okay, y'all? Other questions? I'm feeling okay about this exam? Unfortunately, because we bumped it back, today is drop day. So that does affect you. But if you're still uncertain about the class, you can come see me. We can talk about it, or use the grade calculator online. Okay? So that's an unfortunate effect, but I think that it was the right decision. Right? The right decision of everything you're saying? Okay.
Explain spring 21 is number 6.
Yeah, spring 21, number 6. Electron and proton. yeah, the answer should be B. There's a lot of words there. I have an electron and a proton. They're moving in the same direction, in the same magnetic field, and so they'll feel forces that are opposite one another, because everything's the same. V is the same for them, B is the same for them, Q is the same too, right, because it's an electron and a proton, so they're just going to feel opposite forces. There's just a lot of words there. That's why it might have confused you. And they're moving at 90 degrees. That just means that they're, orthogonal to the magnetic field. Have an electron, have a proton, both moving with a V, the magnetic field. They enter, so it'll feel a force that is out of the page for this one and into the page for that one. Just opposite. Okay? Then we're wrapping up. I will give you credit. Sorry. I know that changed, but we are wrapping up. Okay. I think we're wrapping up. Unless y'all have more questions. Are we wrapping up? Yeah. Which one was that? Okay, do you want me to do the same one I did in class? Does that matter? Okay. Oh, this one? Yeah. So it's probably the first part that's tripping you up, right? Is it the first part? Yeah. Because the second part is just putting in the numbers, right? So I always draw the wavefronts. I try to make this figure big so that you can draw it properly. Draw the wavefronts, and then as I move, I look at my indices of refraction. I know that this one, because it has a small index of refraction, is fast, and this one is slow, right? As the index goes up, my speed goes down, or goes down. So that means this little wavefront that's coming along, it's going to slow down right here. But this side of it stays fast. That's why I said that the twin propeller boat, or the bulldozer, or the tracks, the tank. But that's a good example because you make one side go faster to turn in this direction. So if this side is going faster, the whole thing is going to swing around like this so that my wavefronts are moving in that direction. So that's a great analogy to think about it. And then as I move to the second one, I'm moving from slow to fast. And so I draw my wavefronts again. Now this side is going to swing around like this. So that I bend towards the normal here, and then bend away from the normal here. As I'm moving from low to high to low index. Now you might have a different arrangement of indices of refraction. It might go from low to low, or high to low to high, or even from low to higher. So you can have a different arrangement, but the process is still the same. And then to calculate the angle, let's just using the law of refraction and put it in the values. Even if I'm going from N1 to N3, I don't even need to worry about N2. I can just get rid of that because the law of refraction says that N1 sine theta 1 is equal to N2 sine theta 2, and that N2 sine theta 2 is equal to N3 sine theta 3. So it's true that N1 is equal to the N3. This whole thing that I drew right here. Is it clear? Okay, good. You can do that tomorrow. You'll have to. On the green, so.
Yeah.
Draw the waypoints. Even if it's a little messy, I'll be able to see your rays. Yeah. Go out and get a tractor. Like go drive a tractor or a twin propeller boat. Like that helps? Yeah. Dave is good at all that.
Yeah, you all have to go from the bottom check.
Right, yeah. Okay. Okay, because the index of refraction is 1.2, and when I say fast, it's faster than it is in the second one. because the index of refraction is 1.5, and when my n goes up, that means my speed goes down. If you remember, that is based on our definition of n, that, how did I say it on the equation sheet? Where is that chapter? You'll have this whole equation sheet, by the way. So, yeah, n is equal to c divided by v. So if n is big, that means v is small, and vice versa. There's an inverse relationship. Okay? It's not the easiest exam this semester, that's probably the next exam. But I find that students tend to do better on this exam than they have on the first exam. But don't think, like, if you don't get the right hand rule, you're not going to do well. So make sure you know the right hand rule. Okay, okay? All right. I'm going to pause the video. Don't leave yet. I don't have all your names.